Our last concept for this chapter has to do with isomers, what they are and how to identify them. So first of all, what the heck is an isomer? Well, isomers are molecules that have the same molecular formula but have different structures. So they have the same number and type of atoms, but they're arranged in different ways. Let's take a look at some isomers. First, we have structural isomers. Again, structural isomers contain the same number and type of atoms, but the bonds between those atoms are different so that you get two different structures. Here, for instance, we have two molecules. They have the same number and type of atoms, but they're arranged very differently. This one is arranged as a straight chain, whereas this one has a branch in it. Now, think about this for a minute. What is the chemical formula for this molecule, or for both of these molecules? Well, it's going to be C5, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, C5H12. You could call both of these molecules C5H12, even though they have different structures. Now, because they have different structures, they are going to behave differently inside living systems. Cis-trans isomers are also known as geometric isomers, and they have to do with the arrangement of atoms around a double bond in a carbon chain. So here, for instance, we have two carbons that are bound together with a double bond. Now, the formation of that double bond locks the atoms around the bond into place, so they can't move around once they're there. If the molecule has what we call the cis arrangement, then two of the things connected to the carbon will be on the same side of the double bond. If they have the trans arrangement, then those two things will be attached to opposite sides of the double bond. So cis is the same side, trans is opposite sides. Next, we have enantiomers. Enantiomers are a little bit difficult to describe on paper because they really have to do with the three-dimensional shape of the molecules. They are a type of what's known as stereoisomers. But essentially, enantiomers have three-dimensional structures and are mirror images of one another. So let's think about something that is a mirror image. Well, your hands are mirror images of one another. Take a look at your hands. Your hands have the same basic structures, but they're arranged differently. There's no way that you can put your hands together so that they take up exactly the same three-dimensional space. I mean, try it. Try putting the palms of your hands together. Well, the fingers kind of match up and the thumbs kind of match up, but the backs of the hands are facing away from each other. They're not taking up the same three-dimensional space because they're kind of oriented opposite. If you flip one of your hands over, well, now the backs and the fronts face the same directions, but the thumbs are sticking out on opposite sides. So there's no way that you can arrange your hands in space so that they take up exactly the same three-dimensional space. Enantiomers are the same way. If you look closely at these molecules, you'll notice there's no way you can turn them in space so they take up the same exact arrangement. Now, oftentimes these enantiomers are called left and right. L and D. D is dextral, which means right-sided. Or sometimes you'll see the L represented with an S, which stands for sinestral, which is another word for left. All of these enantiomers are going to be arranged around a central carbon, which is known as the asymmetric carbon. Scientists who design medications have to be very, very mindful of the existence of enantiomers. Even though these types of molecules are very similar to one another, they behave very differently in the body. For instance, here we have two examples of molecules that have enantiomers that behave differently. The top one is ibuprofen. Good old ibuprofen. It's a painkiller. It's an anti-inflammatory. It has a left and a right form. Only the left form is effective as a painkiller. The right form is not. We also have here albuterol. Albuterol is often taken for asthma. It's an anti-inflammatory. In this case, the right-handed form is the effective form. The left-handed form is not. So you really need to understand your enantiomers before you start giving chemicals to people. And the effects of different enantiomers can be very, very different. So you're almost done. Yay! This is your last year turn for chapter 4. On your guided notes, you should find some diagrams of molecules. I want you to look at those diagrams and decide whether they represent structural isomers, cis-trans isomers, or enantiomers, and label them as such. Then I want you to look very closely at those molecules. I want you to find one example of each functional group that we talked about and circle it and label it. Bring this with you to class and we'll look it over. Good job, you guys. We'll see you in class.